Assalamu alaikum. In the last lecture, we derived an expression for torque induced in a current carrying coil placed in a uniform magnetic field. This expression is given by a constant multiplied by cross product of these two vectors. Here, this constant depends upon the geometry of this coil, and V loop is the flux density vector due to current in this coil. We know that a current carrying conductor has a magnetic field around it. In this particular case, we have this coil, rectangular coil, with this direction of current in it, and due to that there will be a magnetic field which will produce flux density vector which will be pointed out of the surface of board in this particular case. In this particular diagram, here, and this Bs is the flux density vector due to these stator poles. What we see is that this induced torque will be maximum when these two vectors are perpendicular to each other. That is, the angle between these two vectors is 90 degrees. That is, if the coil here, this coil, orientation of this coil is like this one. If this coil rotates to this position, then what will be direction of V loop? V loop, direction of V loop can be determined by from the current flows here. So out of the surface of board, that is in this particular diagram, upwards. So direction of V loop, if the coil is placed like this one, is upwards, and direction of Bs is this one. So the two vectors are perpendicular, and corresponding to this situation, induced torque will be maximum. What will be situation when this coil has rotated to this orientation? Then in this particular case, again we can determine the direction of V loop. So direction of V loop is perpendicular to the surface of this coil. That is, both V loop and Bs become parallel or anti-parallel, and in this particular case induced torque will be zero. That is, if the coil is like this one, induced torque will be maximum. If the coil gets rotated to this position, induced torque will become zero. So that is, induced torque is such that it tends to align both the magnetic fields. And if the coil is at this orientation, there will be no induced torque and no further rotation in this coil. So how to keep this coil rotating? One possibility is that we also rotate the stator poles. So as coil gets rotated, we also rotate stator poles, and then the coil will chase the stator magnetic field, and if the stator poles are rotating, the coil will also keep rotating. However, that arrangement is not feasible, because to rotate the stator poles we shall need some another arrangement. In today's lecture, we shall talk about an arrangement which will create a similar effect as if the stator poles are rotating. The arrangement to create a rotating magnetic field consists of a stator. Here we have air space and a stator of ferromagnetic material. On this stator we wind a set of three-phase coils. The first coil is over here. One side of the coil and another side of the coil. At the back end, these conductors are connected. Let's call this coil as A dash. Another coil placed at 120 degrees from this coil, that is over here. and let's call this coil as B dash. These are the sides of the coil. Back side is not visible in this diagram and front side is also not shown. And the third coil is placed at another 120 degrees from this coil. That is, this coil is C dash. So we have a set of three-phase coils on this stator, and these coils are supplied by three-phase currents. That is, the current which is flowing in the coil AA dash, that is given by, and current in coil B dash, that is, and C dash, that is three set of coils supplied with three-phase currents. And we know that a current carrying coil has its own magnetic field. For example, this current IAA dash flowing in this coil will produce its magnetic field. What is direction of this magnetic field? Current is entering from this end and leaving from this conductor. So what is direction of the magnetic field due to current in this coil? We can use the right hand rule. This coil is placed like this one. So current is entering into the coil and leaving from this side. So the magnetic field due to this coil is towards right. This coil is a rectangular coil and placed on this stator. One side of the coil, another side of the coil. At the back end, the two sides are connected. Front end is also not shown. So this magnetic field, let's name it HA dash. The magnetic field due to current in this coil. Similarly, due to current in this coil, there will be a magnetic field. Again, its direction can be determined. This coil is like this one. So direction of magnetic field HB dash. And similarly, the magnetic field due to current in the third coil. So these are the directions of three magnetic fields. What is the magnitude of these magnetic fields? Magnitude of these magnetic fields depends upon the magnitude of the currents in these coils. That is HA dash, that is equal to HM sine omega t, and its orientation is angle 0 degrees. Similarly, HB dash, that is HM, its magnitude is proportional to the current, that is HM sine omega t minus 120 degrees. And what is direction of this vector? Direction of this vector is at 120 degrees. So 120 degrees. Angles of vectors are always measured from this position. So this angle of this vector is 120 degrees. Likewise, the magnetic field strength, magnitude of this magnetic field strength HCC dash, its magnitude is proportional to this current in this coil, and this vector, direction of this vector is at 240 degrees. Due to these magnetic fields, flux will flow, and flux density, we know that flux density is related to magnetic field strength by this expression. So therefore due to this magnetic field, there will be a flux density, let's call it BAA dash, which will be equal to Vm sine omega t angle 0 degrees, proportional to this one. So that proportionality constant is over here. Mu multiplied by Hm is denoted by Bm. Similarly, due to this magnetic field, there will be flux density HBB dash, and that is Vm sine omega t minus 120 degrees angle 120 degrees, and Bcc dash, that is equal to. So what is net flux density in the machine? Net flux density is vector sum of these all these vectors. These are all vectors with magnitude and direction. This vector with magnitude and direction. So net flux density is equal to sum of all these vector sum of all these vectors, and we shall show that the net flux density, magnitude of the net flux density, which is obtained by sum of these vectors, is constant and it will be rotating. So let's show it. Before going to more mathematical and analytical calculations, we do it in a simple way. We find vector sum of these flux densities at different time instants. So let's see what is the situation at t equal to 0. At t equal to 0, what is magnitude of this flux density vector? That is a sine of 0 is 0. So at t equal to 0, b a dash, that is equal to 0. So its direction, what is direction? Angle 0. So we have a vector in this direction with magnitude equal to 0, and bb dash, that is equal to Bm and sine of minus 120 degrees at an angle of 120 degrees, and then Bcc dash, that is equal to Bm sine of minus 240 degrees at an angle of 240 degrees. That is what is a sine of minus 120 degrees? That is equal to minus square root of 3 divided by 2 and multiplied by Bm angle 120 degrees. That is, this flux density vector is 100 at 120 degrees and with a magnitude of minus square root of 3 divided by 2. And the third vector, this vector, sine of minus 240 degrees, that comes out to be equal to square root of 3 divided by 2, and its direction is 240 degrees. First flux density vector, its magnitude is 0, indicated by this dot. This magnitude is minus 3 by 2 multiplied by Bm, and direction is 120 degrees. And third one is magnitude is the same as this one, square root of 3 divided by 2 multiplied by Bm. And we want to add these two vectors. Magnitude equal to minus 3 by 2 Bm, that is equivalent to a vector with magnitude equal to 3 by 2 multiplied by Bm and direction reversed. So how to add these two vectors? You can opt any convenient approach. For example, if you follow the graphical approach, so this is the resultant flux density vector, the net flux density vector, which is equal to B net is equal to B net flux density vector equal to 0 plus minus 3 by 2 Bm at an angle of 120 degrees plus 3 by 2 Bm at an angle of 240 degrees. So you can add these vectors. Graphical approach is over here, and by this graphical approach this comes out to be equal to 1.5 Bm, and angle of this vector is minus 90 degrees. Corresponding to this time instant, we have these flux density vectors, magnitudes and directions, and the net magnetic field, net flux density is sum of these flux density vectors, which comes out to be equal to 1.5 Bm angle minus 90 degrees. We have added the vectors by using graphical approach. Let's analyze the whole situation again at time instant t equal to rather omega t equal to 90 degrees. So what is situation now? BAA dash sine of 90, that is equal to 1. So Bm angle 0 degrees, and B dash, that is equal to sine of 90 degrees minus 120 degrees, that is minus 30 degrees, and sine of minus 30 degrees is minus 0.5 Bm. Direction is 120 degrees. And similarly BCC dash, that is omega t is 90 degrees, 90 minus 240. So sine of this thing 90 minus 240 is again minus 0.5 Bm and an angle of 240 degrees. So at this time instant we can again add these three vectors. The first vector is over here, which is Bm angle 0 degrees. The second vector is minus 0.5 Bm angle 120 degrees. So half of this length with an angle of 120 degrees. So minus 0.5 Bm. So vector with this direction and magnitude equal to minus 0.5 Bm. Likewise, this vector has magnitude minus 0.5 Bm and angle of 240 degrees. So this vector with negative magnitude is the same as a vector with the opposite direction and magnitude equal to 0.5 Bm. And likewise, this vector with negative magnitude is the same as a vector with the polar direction reversed and magnitude taken to be positive, 0.5 Bm. So what is the resultant of these three vectors? This vector plus this vector plus this vector. We can again utilize the graphical approach. So by graphical approach, resultant of these two vectors is this vector. Resultant of this vector and this vector is this vector. We have utilized graphical approach, and now this vector is parallel to this vector. So their vector sum is just the addition of the two. So at this situation, at this time instant, B net comes out to be equal to Bm plus 0.5 Bm, that is 1.5 Bm. What is angle of the resultant vector? Angle of this vector, that is 0 degrees. So corresponding to time instant omega t equal to 0, we have a resultant flux density vector. Its magnitude is equal to 1.5 Vm, angle is minus 90 degrees. At time instant omega t equal to 90 degrees, again magnitude of the resultant flux density vector is 1.5 Vm and its angle is now 0 degrees. We can analyze the situation corresponding to next time instant, that is omega t equal to 180 degrees. Omega t equal to 180 degrees. So what is B A dash? Sine of 180 degrees is 0. So B A dash is 0 and angle of this vector is 0 degrees. And B dash, that is equal to 180 minus 120. What is that? Sine of 60 degrees, and sine of 60 degrees is square root of 3 by 2 Bm, angle 120 degrees. And furthermore, BCC dash, that is sine of 180 degrees minus 240 degrees, that is equal to minus 3 by 2 Bm, angle 240 degrees. And the net magnetic field, again we will use the graphical approach to determine the sum of these three vectors. The first vector has magnitude 0 and an angle of 0 degrees. The second vector has an angle of 120 degrees and magnitude of square root of 3 by 2 Bm. And the third vector, angle of 240 degrees and magnitude of minus 3 by square root of 3 by 2 Bm. What is resultant vector? This vector with negative magnitude is the same as this vector with opposite direction and positive magnitude. And the resultant of these two vectors by using graphical approach is this vector, which comes out to be equal to 1.5 Bm, angle 90 degrees. So what we observe is that at omega t equal to 0, this is resultant vector, magnitude is 1.5 Bm, angle is minus 90 degrees. At omega t equal to 90 degrees, we have this resultant vector, 1.5 Bm, angle 0 degrees. At omega t equal to 180 degrees, we have this resultant vector, magnitude equal to 1.5 multiplied by Bm and angle 90 degrees. That is, magnitude of the resultant flux density vector is always 1.5 and it is rotating. You can even verify it for the next time instant, that is omega t equal to 270 degrees. That is this arrangement of set of three-phase coils placed at 120 degrees from each other and supplied with three-phase currents will produce a uniform rotating magnetic field. This arrangement is exactly the same, its effect is basically exactly the same as if the two poles, north and south poles, placed over here and these are rotated. The resultant effect of this arrangement is the same as this one. So in the next lecture we shall use a more analytical approach to prove the same statement, that is set of three-phase currents supplied to these three-phase windings that generates a rotating magnetic field with uniform magnitude.